Hello. So today welcome to the first training for AI Div. Okay, not the first training, this first deep learning training for AI Div. We'll be moving on from traditional machine learning, and now we're going to be talking about deep learning. So the first and most important topic in deep learning is multi-layer perceptrons. Yeah, and to implement it later, we'll be using TensorFlow and Keras. Okay. Yeah, and please stop me if you have any questions. If not, I will keep going on. You won't understand anything I'm saying. So first, I'll cover multi-layer perceptrons and and basically how they are inspired by biological neurons, as well as the purpose of activation functions. Next, then I will go through like how we train these models using backpropagation. Then after that, I'll go through the TensorFlow Keras API, and then I'll do a demonstration on the fashion amnesty asset or the amnesty asset. I forgot which one I use. Yeah. So first I'll talk about MLPs. So in year three bio you learn about neurons. So neurons have dendrites like this, and this is where they get their inputs. And then the computation happens here in the cell body. And then after they finish like computing, they will send the information down the I think it's called axon, and then they will be received here at the synapses, like at another neuron. So how can we basically turn this biological neuron into artificial one? So basically what we do is that you can view one single neuron as a function. It takes in many inputs, and then it performs some computation and it provides an output. So it's basically a function. And its input is a list of different numbers. So now we need to decide what function we want to use here first. So for for multi-layer perceptrons, this is the function that we use. Basically, each of these inputs has a weight, and then you multiply the weight to the input. So this is basically like how important each of these connections are. And the neuron itself also has its own bias, which is added to the output. And finally, we wrap this whole thing in what we call an activation function, which is a non-linear function. It can be anything that is not just a straight line. And for example, this is one possible activation function. This is the sigmoid function, which we see when you go to the left by a log, it will just tend to 0. When you go to the right by a log, it will tend to 1. And basically what this does is that it introduces non-linearity in the system. And I will explain why this is important later. For now, are there any questions? Okay, I guess that's a no. So these are the different types of activation functions which are commonly used. There's the sigmoid function and the tangent, and the hyperbolic tangent function. And then there's also ReLU, which is rectified linear unit, which is at the start you have nothing, it's all just 0. And then after it ramps up. So this just a line. And then finally you have swish, which is x multiplied by the sigmoid function. This is the best activation function that is currently used for machine learning. So now I'll explain why multi-layer perceptrons are so powerful. Basically, you can stack the neurons like this. So, where's the slide? Yeah, so basically you can stack it in multiple layers like this. So you'll have an input layer, and each one of these nodes receives one input. So this is like in traditional ML, like you're inputting a list of numbers to the model. So this is the same thing. You're inputting a list of numbers to the input layer. Then after that, you have some hidden layers. So here is like it will perform some computation inside. and you can have more layers here. So the model can learn more complicated functions. And finally, there will be an output. So why is this so powerful? So if we go back, you can arrange the simplest configuration you can have is something like this, where you just have a single input and a single output. And then you have a hidden layer with two neurons. So let's say we start by initializing everything like this with zero biases and zero weights, except for like here. Then we find that it's just a straight line. And now if we start increasing the weight of this input, we can find that you can actually make like in this case I'm using the sigmoid activation function. And you can see that you can make the sigmoid more and more like a step function. So basically your neural network, you can form a single step function by adjusting the weights of the network. So after you form the step function, you can also move the position of like the step by adjusting the bias. And when you start adjusting the weight of the other side, you can actually see that you can form like this hump now. So basically you can have a function that goes up and then it goes down. So the idea is that when you have an infinitely large number of neurons here, you can represent any function because any function can be represented with like many of these small bumps. Are there any questions? Okay, so basically this is so a recap. This is how the thing looks like now. So now let's say we want to perform inference. If you just like loop through each of these neurons, it's going to be very slow. So how are we going to do this quickly? So a single perceptron layer is actually quite elegant in that a single multi-layer perceptron layer is quite elegant because you can just express it simply with this formula. So I'll kind of explain what this does now. So first I'll touch a bit on linear algebra. So usually you work with scalars. Like these are just your real numbers. They can be any value. And they just lie on the real number line. Then we have vectors. So in vectors you have learned it's like you stack multiple numbers together. So that forms a vector, basically. So you can view a vector as just being a list of numbers. And then finally we have a matrix. A matrix is you can view a matrix as just a list of vectors or a grid, like a large grid with numbers inside. And basically linear algebra is about forming operations with these things. So one thing you can do with vectors is that you can add them like this. So when you add them like this, you basically take like the first component and you add it to the second component. And then you get x1 plus y1. And like so on. You can also do something called multiplication with them. And this in physics we also use the cross product, but that's not very important here. So we can just focus on what we call the dot product. The dot product basically does an element-wise multiplication of the vector, and then it will sum them. So you get x1 y1 plus x2 y2 plus x3 y3. And finally, this is the matrix multiplication. So when you want to multiply a matrix to a vector, it's a bit more complicated. Actually this was taught in like year 2, I think. Basically, you take this row and you multiply by this row, and then you get your first component. Then you take this one and you multiply by this row again. You get the second component. You take this, multiply by this, and you get a third component. So if we go back now, this is for a single neuron, this is what it looks like. So you can basically consider this sum of the weights and of the inputs to be like a dot product. Because we can express the weights like W1, W2, and W3 We express it in one vector. We call it W. And we can express the inputs in another vector. So this is like the vector X. So now if we take the dot product of W and X, which if you look previously, is basically doing an element-wise multiplication and then summing everything. So that's basically what is happening here. So you can take a dot product. So this gives you the function for a single neuron. And now in a layer, you have like many neurons. So what happens now is that you are basically repeating this multiplication across each neuron. That means your vectors now become matrices. So for example, this bias here becomes a vector, and then the vector W, which is the weights, becomes the matrix. Because if you remember previously, a matrix here is just it's just a list of vectors. Like this is one vector, this is another vector, this is a third. So basically, after you stack like all of these operations together, you can get this expression for the perceptron layer. And this is actually quite elegant because computers, particularly GPUs, are very good at matrix multiplication. So if you can express the inference of the network using matrix multiplication, you can actually evaluate it very quickly. Yeah. Are there any questions? I will take that as a no. Okay. So now I'll explain how we can basically optimize these networks to work like this, to basically like fit the training data. So first we need to define something called the loss function. And what we define as loss function, basically it describes how well the model is performing. So the model is going to be evaluated on the data and it will give some prediction. So basically it measures like how far away your prediction is from your ground truth. So for classification, we usually use loss functions like binary cross entropy and categorical cross entropy. And for regression, we usually use things like uh, the mean absolute error or the mean squared error or the root mean squared error. So like these measure the difference between the predicted and the ground truth. Like and then you sum over all of the pixels or all of the values within the data. So I'll give a brief explanation of backpropagation without going into too much math. So basically, if you look again, this is the function. This is the MLP, and each each of these edges and each of the neurons has either a bias or a weight, and we can take all of these together and we can call them the parameters of the model. So what we want to do in backpropagation is to optimize these parameters to get them to minimize the loss function. Because when the loss function is minimized, it means that the model has successfully fit the function. So basically what you can see here is that these are the weights or the parameters of the model, and these are the new weights of the model. And what we're doing here is called gradient descent. So uh, basically we have this thing called the gradient. So this even if you don't understand what this symbol means, basically this part of the expression means that you're taking the gradient of the cost function at a certain point in the optimization landscape. This means that, for example, if okay, so let's say I have a function that looks like this. and the model is like now here. This gradient will point downwards, it'll point this way, and the model will keep going down and keep following the gradient until it reaches the bottom. So this is an optimization method which we call gradient descent. And the speed at which it goes down is determined by this parameter called the learning rate. And it's quite important to get the correct value for the learning rate. So you can kind of imagine what happens if this is too small, too big. So if this is too big, for example, then the model would be here. And then because its gradient is telling it to go like downwards by a lot, it will overshoot and maybe it'll end up like here. And then it will like oscillate a lot within here. But if the learning rate is too small, then what could happen instead is that it will just take very long and slowly go down like this, which is also not really what you want. So you should tune this learning rate accordingly so that the model will take the least time to converge. Okay, but a problem with gradient descent is actually that the loss landscape can have many local minima. So, for example, if we look back at this model that we were looking at previously, and let's say I wanted to fit this function, we can see that for different initializations of the parameters, like it can obtain very different results. Like for example, here it has fit this not very good curve to the function, but in this case, it has fit this very nice curve to the function. So this shows that like it won't always converge to the same minima, and even if it converges to the same minima, that minima might be a local minima rather than a global one. Because you can imagine that the optimization space could have like multiple bumps, multiple minima like this. So if the model, for example, starts here as compared to starting here, like if it starts here, then it will go in like this. But if it starts here, then it will perhaps go here. And this is suboptimal because this has a higher loss than this. And this is what we don't really want. So there's a lot of methods that people have tried to develop to try and prevent the model from only going to the local minima. And you can also see it like here, because over here I plotted the loss landscape in the neighborhood of this model's weights after it has converged. You can see that the loss landscape here and the loss landscape here looks very different. So this also shows like how gradient descent can reach different local optima that basically look different and produce different results. Yeah, and I have more examples here. So you can see that the model has fitted this line to this function, while in other cases you can fit a much better line. Are there any questions so far? Yeah, to fit more complex functions, you need more neurons. Okay, so now I'll talk about the issues with gradient descent. So if you can recall, this is the formula. This is the current weights, and this is the new weights. And this is the gradient. So yeah, this is the issue, right? So it will get stuck in local minima. So over here, there's this animation that I made of gradient descent. And you can also see that when it's at a position like this, it takes very long to go down this ridge. So this is another issue that we want to try and fix. So one thing that has been tried in order to fix this is something called momentum. So in physics, there's this idea of momentum where basically an object, if you make it start moving, it will take effort for you to make it stop moving. So this is kind of the same thing. Basically, it allows the thing to keep moving, although the gradient tells it to stop moving. So this is the momentum, and alpha controls how strong the momentum is. So you can imagine this is an animation of different values of momentum, and you can see that they actually oscillate now. So this is actually quite similar to like if you roll a ball down this thing, you'll notice that the ball will also oscillate. So it's very similar. But now the issue is that the oscillations here are quite large, and having very large oscillations is also not very desirable because okay, PowerPoint is lagging. Are there any questions so far? Okay, PowerPoint down. Okay, so basically, so the solution to this is something which we call uh Neskarov momentum. Basically what happens is that instead of computing the gradient at where the move at the current position, you compute it at its new position, considering the impact of momentum. And you can see that this actually makes the oscillations dampen out a lot more quickly. And this is actually pretty good because then it's less likely to overshoot the minima, which we still want it to go into. And there's also more complicated optimizers after this, like Adam and Lion, but I won't be talking about them today. So before I talk about the implementation, the last thing I talk about is batching. So it's very it'll take a long time if you want to compute the gradient over a portion over the whole data set, because then you have to look through the whole data set. And because this takes so long, models usually do something called batching, which is that within one epoch, which basically is the amount of time it takes for the model to go through the whole training data set, you will split the training data set into things called batches. And batches is basically like you're basically cutting it up, and each batch has a certain size. Usually we use a batch size which is a power of 2. And basically whenever it goes over a single batch, it will evaluate the gradients and perform a single gradient descent step. So this is a lot more efficient because then you can have more training steps within a single epoch. And at the end of the epoch, you're also running it on the validation data. So this will show how well the model is generalizing, because I think previously Zion has mentioned about overfitting. So using the validation data allows you to evaluate whether the model is overfitting to the training data. Yeah. And the batch size is actually also a pretty important parameter. It affects how fast the model converges. For example, if you use a bigger batch, the convergence is more stable because the variance between each batch will be smaller. And so like the gradient descent will be like more directed in a sense. Whereas if you use a smaller batch, the training will be a lot faster because you can form more gradient descent steps in one epoch. Yeah. Okay, before I move on, are there any questions? I will take that as a no. Yeah, so now talk about TensorFlow and Keras. So basically, TensorFlow is a low-level library, was developed by Google. And Keras is a high-level library, and then basically Keras can interface with TensorFlow quite well. So when you want to build a model, which is build a deep learning model in Keras, there are three different ways to do it. There's the sequential API, which is basically like you stack the layers on top of each other. So each of these is a single multi-layer perceptron layer. So like these two are your hidden layers, and this is the output. Whereas this would be the functional API. So this is a lot more flexible because unlike the sequential API, let's say you want something that looks like that isn't just this. So for the sequential API, it's just like this, and then we'll just go through them in sequence. Whereas for functional API, you can, for example, have something that looks like this. So like you can go into separate branches and then they can come back like this. So you will use the functional API for models where the thing is not really like aligned. So this sort of more complicated type of model will come up later when we talk about CNNs. So finally, after you define the model, you also need to build the model. So how you do this is that, so first you build the model like this. So this, you are basically specify the model's architecture. You can specify a number of units within the layers and the activation function. So then next, you can compile the model. And then finally, you can fit it. And then like when you compile it, you can specify the optimizer and the loss and like what other metrics you want to evaluate it by. Like for example, here you can evaluate it by accuracy. And when you're fitting it, you pass in the data as well as the number of epochs to train for and the batch size. Okay, are there any questions before I do the demonstration? I guess that's no. Okay, let me switch to Google. You can see the notebook here. I will send the link. Okay, so now I'll talk about making a simple MNIST MLP. So first we have to import the libraries. So we import NumPy as well as TensorFlow and Keras. Okay, so basically now we can see the number of, okay, I'll explain what MNIST dataset is first. So the MNIST dataset is basically a a bunch of images of numbers. So it looks like this. It's many handwritten numbers. So basically there are 10 classes. You can go from 0 all the way to 9. So we specify here the number of classes is 10, and the input shape is 28, 28, 1, which means that each image, because they're all images, so it's not a single vector, but it's more like a matrix. So 28 by 28 means it's 28 by 28 pixels, and then it has 1 for the number of channels, because the images are grayscale. Because for normal images, they actually have 3 channels, which is the red, green, and blue, and that's what gives them color. So in this case, they're grayscale images, so we use 1. So next, we just load the data straight from Keras datasets. And then we normalize the images. So normalization can usually help in machine learning because it makes all the values between 0 and 1. So all of the different inputs in the model are within the same range. So the model is not inherently biased to give one parameter more weight than the other. Yeah. So then after that, this is basically just adjusting their dimensions. And we also have to convert the class vectors to binary class matrices. What this means is that each of these before this was expressed in 0 or 1 or 2. But for our model, the model can only output, it'll be much easier for the model to output 1 or 0 instead of like 1 to 9. So what we do is something called one-hot encoding. Yeah, what we do is something called one-hot encoding, where basically like for example 0 gets converted to 1, 0, 0, 0, 0, 0, 0. Yeah. So basically if the first one is 1, this means that the class is 0. And there are 10 zeros and there are 10 values because there are 10 classes. And basically it looks like this. So like 1, then your 1 will get moved to here. Or like for example 6. It's here. Yeah. So this is how one-hot encoding works. So now we can actually build the model. So, and before we pass the image directly into the MLP, recall that the MLP it can only accept a vector, and because the image is two-dimensional, it's a matrix, we cannot pass it indirectly. So what we do first is that we have a layer called flatten. So this converts the 28 uh 28 by 28 image to a this many pixel this many value vector, dimensional vector. Yeah. And then after that we can pass it through the 2 hidden layers, and then finally it will output the output layer, and we're outputting num classes because as mentioned before, the thing is using one-hot encoding. And activation for this one is also called softmax. How the softmax activation works is that a very high level way of saying how the softmax activation works is that basically each thing that outputs is the probability of that that class being the correct class. Yeah. So then when you call model.summary, it will give you like a very nice summary of how the model looks like. And after that, we can basically train the model. So you can see here that before fitting it, you have to compile the model, and you can also tell it what optimizer to use and what metric to measure by, other than the loss. So you can see here the model trains quite quickly because it's quite small. And also achieves quite a high accuracy on both the training and validation data set. So It shows that the model isn't really overfitting. Yeah. And the last thing you can do is you can evaluate it on the test set. So for usually we split it into three. We split the data set into training, validation, and test. So training and validation is used during the training process. Every epoch, the model is evaluated once on the validation data set to get some amount of accuracy. And before you finally deploy the model, you will pick the epoch with the highest validation accuracy or whatever parameter it is that you are evaluating on, and say that that is the best model that you want to use. But make sure that you're not overfitting on the validation dataset in that case. You basically evaluate it again one more time on an unseen test dataset to make sure that the model can perform well on unseen data. And basically this is what we're doing here. Yeah, and you can see the output. It outputs a loss and an accuracy. Are there any questions? Okay, I think that is a no. So there's one more thing I will touch on before I end this session. Okay, so in the spirit of research, I'll give you some homework. Basically, this is so to recap, this is what MLPs look like if you have forgotten already. Right, like this. Okay. We call this the width of the model, and we call this the depth of the model. The depth is number of layers in the model, and the width is the number of neurons, sort of the number of neurons in each layer. So as homework, you can try and answer these questions. Like how will changing this width affect the performance? And how will changing the depth affect the performance? And finally, how can we fairly compare different models of different architectures? Is there a way we can reduce the whole model, like the capacity of this model's ability to learn down to a single parameter? So that if I have the two different architectures that both give like the same number, it is fair for us to compare them to see which architecture is better. Yeah. And if you choose to do the homework, I will give you purple candy. Yeah. I'll send the screenshot. Yeah, are there any questions?